Welcome to the deep dive. You send us your curiosity and, yeah, some really fascinating sources, and we've dug into them for you.
We certainly have.
Today, we're jumping headfirst into the world of stars that aren't actually alone, non-single star systems.
Right. Pairs, triples, maybe more.
And our main guide for this is the incredible data coming from the Gaia space mission, specifically its third big data release, DR3.
Yeah, we've been looking at a scientific essay that really unpacks what Gaia is finding. It's pretty amazing stuff.
So our mission, if you will, for this deep dive is to uncover the surprising discoveries and advancements Gaia is bringing, how it's changing our view of stars with companions.
And you should definitely stick around because the sheer variety is kind of mind-blowing. We're talking other stars, of course, but also brown dwarfs and maybe even black holes.
Okay, black holes. We'll definitely get to that. But maybe let's start with the basics. Finding stars that aren't single isn't exactly brand new.
Oh, no, not at all. Astronomers have been clever about this for, well, over a century.
How did they do it before Gaia?
Several ways, really. Sometimes you can literally just see two stars close together in a telescope, visual binaries.
Okay, straightforward enough.
Then there's the astrometric method. You see a star doing a little wobble, a back and forth dance on the sky.
Ah, because something unseen is pulling on it.
Exactly. Then there's spectroscopy. You look at the star's light, its spectrum, and see the lines shifting back and forth. Doppler effect.
As it orbits something else.
Precisely. And finally, the ones maybe people have heard of, most eclipsing binaries.
Where one star passes in front of the other from our point of view?
Yeah, and you see these telltale dips in the brightness. So lots of methods, but often painstaking, one system at a time.
Right. So what makes Gaia such a game changer then?
It's the scale and the precision. Gaia is measuring the positions, the astrometry, and the brightness of photometry of, like, billions of stars.
Billions. Wow.
And it's doing it with accuracy we've just never had before.
Mm-hmm.
So it can find and characterize all these different types of non-single systems simultaneously all across the sky in a really uniform way.
So it's not just finding more, it's finding them better and more systematically.
Exactly. It's like upgrading from a magnifying glass to look at ants to, I don't know, satellite imaging for the whole planet.
Okay, that's a powerful analogy. Now here's something that caught my eye in the source material. Something as basic as a star's mass. It's actually really hard to measure directly.
It is. It seems like it should be simple, but yeah. And mass is the fundamental property of a star.
Why is that?
Well, it governs everything. Its temperature, its brightness, how long it lives, how it dies. Its entire life story is basically dictated by its mass.
Okay, so super important. Why is it hard to weigh a star then?
Because gravity is what we measure, right?
Yeah.
And you need to see how a star's gravity affects something else.
Ah, so you need a companion, a binary system.
Bingo. That's the only direct way. You measure how long they take to orbit each other, the period,
Okay.
and how big that orbit is, the semi-major axis. With those two things, and Kepler's laws, you can calculate the total mass of the system, m1 plus m2.
But that sounds tricky too. You need to know the distance really well.
Extremely well. The calculation is super sensitive to errors in distance, the parallax, and also how accurately you measure that orbit shape and size. Tiny errors get magnified.
Okay, so that's the total mass. Getting the individual masses must be even harder.
It is. You need special circumstances, specifically systems we call double-lined spectroscopic binaries, SB2s.
Double-lined, meaning?
Meaning you can see the spectral lines from both stars in the spectrum, and you see both sets of lines shifting back and forth as they orbit their common center of mass.
Okay, I see.
To get the individual masses, you need to combine that spectroscopic info, which tells you how fast they're moving towards and away from you, with the astrometric data from Gaia.
The wobble across the sky.
Right. That astrometry tracks the motion of the whole system.
It feels like putting puzzle pieces together. You mentioned there are some orbital details you can get from both methods.
Yes, exactly. 4 key parameters overlap: the orbital period, the shape or eccentricity e, the orientation of the orbit omega, and a reference point in time TOR. You can derive these from both the spectroscopic data and the astrometric data.
So that helps confirm things.
It does. And critically, in those SB2 systems, the spectroscopy gives you the ratio of the masses.
Okay, how much heavier one is than the other?
Correct. But to get the actual individual masses in kilograms or solar masses, you need one more piece: the inclination.
How tilted the orbit is relative to us.
Exactly. Is it face on, edge on, somewhere in between? That inclination comes from the astrometric orbit measured by Gaia. Once you have the mass ratio and the inclination, boom, you can calculate M1 and M2 separately.
That's clever. So Has Gaia actually done this yet? What are the results?
Oh yeah. Just from the DR3 data alone, using this combo of astrometry and SB2 orbits, astronomers nailed down the individual masses for about 70 stellar components that hadn't been measured before.
70 already. That's
Yeah,
significant.
it really is.
Mm.
And that's just the beginning. The real potential um, comes when you start combining Gaia's astrometry
Right.
with huge ground-based spectroscopic surveys,
Right.
like APOG, for example.
Hmm.
Its latest data release has over 8,000 SB2 systems in it. Imagine combining Gaia data with all of those.
Wow, okay. The potential is enormous.
Definitely. Even back with Gaia's predecessor, Hepgarkos, combining his data with just 7 SB2s showed this potential. Gaia takes it to a whole new level.
All right, let's shift gears a bit. Brown dwarfs, these kind of failed stars. There's something mentioned about a desert.
Ah, yes, the brown dwarf desert. It's a fascinating story. See, back when radial velocity surveys first started hunting for exoplanets,
By looking for the wobula caused by an orbiting planet.
right, they also thought, hey, we should find loads of brown dwarfs this way too. Objects bigger than Jupiter but smaller than stars, maybe 10 to 80 times Jupiter's mass.
Made sense. They'd cause a bigger wobble than a planet.
Exactly. Finding them would have been really important for testing theories about how stars and planets form and how these intermediate objects fit in.
The desert implies they didn't find many.
Not where they expected them most, they found surprisingly few brown dwarfs in relatively close orbits, say, within 3 or 4 astronomical units, like out to Mars, or the asteroid belt in our system around stars like our Sun.
Huh. Why a desert?
That's the puzzle. Subsequent surveys confirmed it. They did find brown dwarfs further out, with orbits taking maybe 10 years or more, but in that intermediate zone. Very sparse.
So how many did we know about before Gaia really got going?
Around Sun-like stars, F, G, K types, maybe only about 100 confirmed brown dwarf companions were known in total.
Just 100. That does sound low. So what were the predictions for Gaia?
People ran simulations based on Gaia's expected precision, because it could detect that tiny astrometric wobble even from a lower mass companion like a brown dwarf.
Right.
The predictions were huge, maybe 30,000, perhaps even up to 50,000 brown dwarf discoveries.
50,000 compared to 100 known before.
Yeah, a massive leap was expected.
Has Gaia delivered? What's DR3 showing?
Well, the early results are definitely pointing that way. One study analyzing DR3 reported finding over 1,800 brown dwarf candidates just from the astrometry.
1,800 candidates already?
And get this, only about 10 of those were previously known from the radial velocity surveys.
Wow, so Gaia is finding almost entirely new ones.
Seems like it. And it allows us to start putting numbers on things. For example, one estimate suggests that around low-mass M-dwarf stars, the frequency of brown dwarfs with periods less than 1,000 days might be around 0.3%.
Still low, but now we have a number based on many more examples.
Precisely. It's a huge jump in our census of these objects.
So Gaia is really populating that desert, or at least finding oases we didn't know about.
You could say that, yeah. It's dramatically changing the picture.
Okay, so Gaia finds stars, it finds brown dwarfs. What else can this wobble watching technique reveal? I saw the term compact companions. What does that cover?
All right, this is where it gets really cool. The key thing is, Gaia detects the motion of the star it sees. That motion is caused by the gravity of whatever's orbiting it.
Regardless of whether the companion emits light?
Exactly. It doesn't matter if the companion is bright or completely dark. If it has mass, it causes a wobble, and Gaia might see it.
So what kind of invisible or faint things are we talking about?
Oh, brown dwarfs we just discussed. But also white dwarfs, those super dense cores left behind when stars like our sun die.
Okay.
Planets, of course, though, finding those with Gaia astrometry is generally harder, unless they're massive and far out. And then the really exotic stuff. Neutron stars, maybe even black holes.
Remnants of massive stars.
Correct. And the Gaia DR3 astrometric orbits are already giving us the first hints of candidates in all these categories.
How do you tell them apart if you can't see the companion? How do you know if it's a white dwarf or a neutron star?
It's tricky. One tool they use is something called the astrometric mass ratio function. It's a bit technical, but basically
This is the gist.
it combines the inferred mass ratio from the orbit with the luminosity ratio. If the companion is really faint compared to the primary star, that helps constrain what it could be.
I see. So if the wobble implies a certain mass, but you see basically no light from the companion, it points towards something dense and faint.
You got it. And when they looked at the distribution of inferred companion masses for over 700 of these compact object candidates from DR3,
Yeah. What did they find?
A really noticeable peak. Concentration of mass is right around 0.6 times the mass of the sun.
And that's significant because...
Because that's bang on the typical mass for white dwarfs that we see out in the galaxy.
Ah. So Gaia seems to be uncovering a huge population of binaries where one star has already died and become a white dwarf.
That's the strong implication. The prediction is that Gaia could end up increasing the number of known binary systems with white dwarf components by maybe a factor of 10, maybe even more.
That's incredible for studying stellar evolution endpoints.
Absolutely. And it doesn't stop there. Remember the spectroscopic binaries where you only see one set of lines, SB1? If you find an SB1 where the calculations imply a very large minimum mass for the unseen companion, what they call a large mass function, then you start thinking, maybe it's not a normal star or a white dwarf. Maybe it's something heavier.
Like a neutron star or a black hole.
Potentially, yes.
Yeah.
Those are the candidates you'd look at closely.
Any actual black hole candidates popping up yet? You mentioned it earlier.
There's one tentative, very interesting example mentioned in the source, a star called HIP 15429.
Okay.
It looks like a massive bright star, a B5 supergent, and the orbit suggests its unseen companion is very massive indeed. Could be a black hole.
Could be. Sounds like there's a catch.
Well, yes. Science is cautious. The researchers point out there could be other explanations. It might be an algol-type system where weird mass transfer is happening, or maybe it's not even a binary, but a triple system, and the complex gravity is fooling us.
So more work needed on that one.
Definitely. Needs more detailed follow-up observations, to be sure. But it's a tantalizing hint of what Gaia might uncover.
It really paints a picture of Gaia as this multi-talented observatory. It's not just positions, it's brightness over time, and for brighter stars, even radial velocities. How does putting all that together help?
It's incredibly powerful. You know how the Kepler mission totally changed exoplanet science? Just by staring at stars and measuring brightness very precisely.
Yeah, finding all those transits.
Right. Gaia is doing something analogous, but by combining its amazing astrometry with its multi-epoch photometry measuring brightness repeatedly over years and its radial velocity measurements. This synergy lets us tackle problems we couldn't properly address before.
Okay, give us an example. How does this combo work in practice?
Well, one challenge is telling apart a genuine single-lined binary in SB1 from a star that's just pulsating, a long-period variable.
Because both can show changing radial velocities.
Exactly. The star's surface expanding and contracting can mimic the Doppler shift of orbital motion.
So how does Gaia help sneak that out?
Gaia's photometry comes in. If the star shows periodic changes in brightness that match the radial velocity period, that strengthens the case for pulsation. There's no corresponding brightness change, or it's different, maybe it really is in orbit. The paper mentions several cases where Gaia helped resolve this ambiguity.
Okay, that makes sense. Using light variations is another clue. What about these ellipsoidal variables? Sounds like stretchy stars.
Yeah, basically. These are really close binaries. So close that their mutual gravity distorts them from perfect spheres into, well, ellipsoid shapes, like rugby balls or eggs, kinda.
Seriously?
Yep. And because they're distorted, even if they don't actually eclipse each other.
Because the orbit isn't perfectly edge-on.
Right. Even then, as they orbit, the amount of surface area we see changes, and maybe the surface brightness isn't uniform, so the total light we get from the system varies periodically.
Subtle brightness changes just due to the shape and orientation changing.
Exactly. Usually small variations, maybe just a few %. Yep. But Gaia can pick them up.
And you mentioned these pop up in exoplanet studies, too.
They do. The Kepler telescope actually saw these ellipsoidal variations in the star HATP7, which has a massive hot Jupiter planet orbiting very close. The planet's gravity was slightly distorting the star.
Wow. So Gaia sees this in binaries.
Yes. And sometimes a star might have been initially classified as a pulsating long-period variable, but then Gaia's astrometry finds an orbital period, and they notice the brightness variation period is exactly half the orbital period.
Half? Why half?
Because the distorted star shows its elongated profile twice per orbit. That pattern is a key signature of ellipsoidal variation. VPhys 540 SIG is an example they give where it was reclassified this way.
And if the brightness period matches the orbital or RV period,
then it's more likely to be a genuine pulsating star, not an ellipsoidal effect.
Clever distinction. What were these phase lag binaries? Sounds mysterious.
It means there's a consistent time difference, a lag between when the brightness variations happen and when the orbital motion from spectroscopy or astrometry says they should happen, if that makes sense. The peaks don't quite line up.
Okay. Why would that happen?
One leading idea is star spots. Imagine one star in the binary has a big dark spot on it, maybe like sunspots, but larger or more persistent. And maybe the star's rotation is locked, synchronized with its orbit.
So the spot always faces the same way relative to the other star?
Possibly. As the star rotates, the spot comes into view and goes out of view, causing a dip in brightness. But maybe the spot isn't located exactly where you'd expect based purely on the orbital geometry. That difference could cause the phase lag.
So it tells you about surface features on the star?
Potentially, yes. About the location and maybe even the lifetime of star spots in these tidally locked systems.
Fascinating. Okay, one last category mentioned. ELCVN systems. Sounds like a specific type.
They are Eocane Venaticorum systems. They're a specific, quite rare type of short-period eclipsing binary.
What's the configuration?
Usually you have a relatively hot main sequence star, maybe an A or F type, and orbiting it very closely is a low-mass, pre-helium white dwarf.
A white dwarf that hasn't started fusing helium yet.
Well, it's the remnant core of a star that never got hot enough to ignite helium, often after losing its outer layers. These ELCVN systems are thought to be a product of some serious mass transfer between the two stars earlier in their lives.
So they represent a specific, maybe short-lived evolutionary stage.
Exactly. The star that's now the white dwarf probably dumped a lot of its outer envelope onto the companion, which is now the brighter AF star we see.
And Gaia is helping find or understand these two.
Absolutely.
Yeah.
They give the example of HD 23692. It's fairly right, about 9.5 magnitude. Gaia's data, both the light curve from the eclipses and the radial velocity curve, shows something characteristic.
Which is?
The deeper eclipse happens when the smaller, fainter secondary star passes in front of the brighter primary.
Wait, usually the deeper eclipse is when the brighter star is blocked?
In most eclipsing binaries, yes. But in ELCVN systems, the secondary, the pre-white dwarf, is actually much hotter than the primary, even if it's smaller and less luminous overall. So when it gets eclipsed, you lose more light per unit area. Oh, wait, I misspoke there. Let me correct that.
Ah, okay.
The deeper eclipse is typically when the hotter object is eclipsed. In ELCVN, the secondary pre-white dwarf is much hotter. So when the cooler, larger primary passes in front of the small, hot secondary, that's the deeper eclipse. My apologies.
Ah, okay. That makes more sense. The small, intensely hot thing gets blocked.
Exactly. And they even see evidence for this temperature difference in Gaia's different color filters. The secondary eclipse looks deeper in Gaia's blue filter GBP than in its red filter GRP.
Because the secondary is hotter and thus bluer.
Precisely. It's a beautiful confirmation of the nature of these systems, combining photometry and radial velocity.
Wow. Okay, so summing this all up, it feels like Gaia isn't just adding data points. It's fundamentally changing how we see binary and multiple stars.
I think that's fair to say. It's providing this huge, uniform data set that lets us study everything from basic stellar masses to these weird brown dwarfs, white dwarfs, and maybe even more exotic things.
And uncovering the details of things like ellipsoidal variations and specific evolutionary pathways like ELCBN systems.
Yeah, the sheer breadth of discoveries is remarkable.
And it really seems to be the combination of Gaia's different capabilities, the positions, the brightness changes, the velocities that unlock so much.
Absolutely. That synergy is the key. It allows us to connect the dots in ways that were much harder or even impossible before. We're not just counting stars, we're understanding the complex physics of their interactions.
This has been a really illuminating deep dive into what Gaia is teaching us about stars that aren't alone. It really makes you stop and think, doesn't it?
It does.
I mean, if so many stars actually have companions, maybe most of them, in some mass ranges, how does that change our bigger picture, our understanding of how planets form around these systems, or even how entire galaxies evolve over cosmic time?
This is a fundamental piece of the puzzle. You can't ignore that a huge fraction of the building blocks, the stars, are in these complex relationships.
What other surprising connections or weird phenomena might be lurking in future Gaia data releases as we look even closer at these stellar partnerships? It definitely leaves you wondering.
There's certainly more to come.
Well, that's something for you to ponder. Thanks for joining us for this deep dive.